All right, welcome to Next Gen Manufacturing. We're living in this world that's built from some pretty incredible materials. I mean, stuff that's lighter and stronger than anything we've ever had before. You'll find it in our airplanes, in our wind turbines, even in Formula One race cars. It's literally shaping our future.
But that brings up a really interesting question, right? I mean, if these materials are that tough, that advanced, how in the world do you actually cut them? How do you drill them and shape them with any kind of precision? Okay, so let's get into it.
So here's how we're going to break it down. We'll start with what I'm calling the Composite Conundrum, basically why these awesome materials are such a pain to work with. Then we'll check out the first attempts, the brute force methods, and then get into the really cool stuff, the next-gen light and water solutions. And finally, we'll wrap up by looking at what all this means for the future of, making things.
Okay, first up, the Composite Conundrum. So the heroes of modern engineering, they're these materials called composites. They give us just incredible strength, but without all the weight you get from normal metals. The catch? Well, this strength comes at a price. They're an absolute nightmare to machine.
And here's the heart of the problem. A composite isn't just one single thing, like a block of aluminum. Think of it more like a team of materials all working together. You've got this softer polymer resin, which is kind of like the glue, holding together this whole network of super strong, really hard fibers, like glass or carbon. And trying to cut both of those things at the exact same time? Yeah, that's where all the trouble starts.
Right, so this unique structure is exactly why these wonder materials seem to actively fight back when you try to shape them. And it really all boils down to two key properties.
The first one is called heterogeneity. And yeah, I know it's a fancy word, but the idea behind it is actually pretty simple. Just imagine you're trying to slice a cake. But this isn't just any cake. It's got layers of soft sponge, but it's also packed with steel bolts and uncooked spaghetti. A knife that's perfect for the sponge is going to be totally useless against the bolts, right? Well, that's what's happening with composites. You're never just cutting one thing, you're trying to cut everything at once.
Okay, the second property is anisotropy. So inside a composite, those strong fibers, they're all lined up in various specific directions. The best way to think about it is like the grain in a piece of wood. It's super easy to cut with the grain, but the second you try to cut across it, the wood just splinters and tears, right? Well, composites do the exact same thing.
So you combine these two properties, and you get four massive headaches for any engineer trying to work with this stuff. First, those abrasive fibers just chew through steel tools like they're nothing. Second, composites are great insulators, which sounds good, but it means heat builds up like crazy during cutting and can literally burn the material. Third, the sheer force of cutting can peel the layers of the composite apart. They call that delamination. And to top it all off, the dust you create can be abrasive, or if it's carbon fiber, it can even conduct electricity, so it's a hazard for both people and the machines.
So what was the first solution engineers came up with? Well, pretty much just brute force. They decided to stick with conventional machining. Drills, cutters, the usual suspects. But they had to make some serious upgrades just to have a fighting chance.
And that first line of defense was just make the tools harder. Your standard high-speed steel, it just gets eaten alive, completely useless. So they moved up to carbide tools, which offered a much better balance between cost and how long they'd last. But for the really tough jobs, the only thing that could possibly stand up to that constant abrasion was diamond-coated tools, which, as you can imagine, were by far the most expensive option.
But here's the thing, even diamond tools have their limits, because some fibers, like the aramid fibers you find in stuff like Kevlar, they have a special trick up their sleeve. They don't just break cleanly when a sharp edge hits them. Nope, they're just too tough for that. They fight back.
And this is what you get. Instead of a nice clean cut, the aramid fibers just get pushed around and torn. It leaves this fuzzy frayed edge. It's not a clean slice at all, it's more of a ragged tear. And this isn't just about looking ugly. It can completely destroy the precision of a critical part. And just to give you a sense of how extreme this fuzzing can get, check this out. Engineers have actually reported that after drilling, say, a 10mm hole in an aramid composite, the fuzz from all those torn fibers can actually spring back and completely cover up the hole, so it's basically invisible once you pull the drill out. That's how much this material fights back. At this point, it was clear brute force just wasn't going to cut it. Literally.
Okay, and this is where the story gets really cool. To solve these problems, engineers had to think way outside the box. They had to think beyond a physical tool actually touching the material. What they needed was a non-contact solution. And so, they turned to two of the most fundamental things in nature, light and water.
First up, let's talk about lasers. The principle here is just pure physics, really. You take a gas, you energize it, and you create this incredibly powerful focus beam of light. A series of mirrors guides that beam down to a cutting head, and then a lens focuses all that energy onto a single microscopic point. The heat is so intense, it doesn't just melt the material, it instantly vaporizes it. It just turns it from a solid straight into a gas. No tool wear, no cutting forces, just pure focused energy.
The other solution is just as cool: water jet cutting. With this, you take plain old water and you use a massive pump to pressurize it to absolutely insane levels. Then, you force all that high-pressure water through a teeny-tiny nozzle, often made of sapphire or diamond, and what comes out is a needle-thin jet of water moving at supersonic speeds. This isn't about heat like a laser, it's pure mechanical force. It's like a tiny, super-controlled erosion that just slices right through the material.
And look, when I say supersonic, I'm not kidding. That jet of water is moving at over 900 meters per second. That's more than twice the speed of sound, Mach 2. It's just an incredible amount of focus power, and it can cut through materials that would absolutely shred a normal drill bit.
And when you put these new methods side by side with the old way, the advantages are just crystal clear. Water jet cutting? It creates zero heat, which is a huge deal for heat-sensitive materials. Lasers? They have absolutely no tool wear. None. Plus, they both basically solve the dust problem, and you need way less force to clamp the material down. They directly fix all the biggest problems that came with conventional machining.
So what does this whole journey, from a tricky material science problem to these incredibly advanced solutions, really tell us about the future of manufacturing?
Well, when you boil it all down, the takeaway is actually really simple. Next-generation materials demand next-generation tools. As we invent stronger, smarter, more complex materials, we just can't expect to use the tools of the past. Progress in what we make demands progress in how we make it. Brute force has to step aside for precision energy.
And that kind of leaves us with one final thought, doesn't it? I mean, we've gone from hardened steel to diamonds to focus beams of light and supersonic jets of water. So as the materials we create become even more intelligent, even more complex, what's next? How are we going to shape the truly unimaginable materials of tomorrow? Thanks for joining me.